Hello everyone, this is Sarita, Assistant Professor of Chemistry, GDCW Begumpet. I welcome you all to my next session, that is spectroscopy. Suppose if we have any unknown compound, how do you determine the structure of that particular unknown compound? Generally, we go for either chemical methods or physical methods. So chemical methods where we use different chemicals or reagents to know the structure of the compound. Whereas under physical methods, we can go for spectroscopy. So today, let us deal with spectroscopy, the principles involved in spectroscopy and about Lambert-Beers law. So what is spectroscopy actually? Spectroscopy is nothing but how the matter interacts with the light. So we can define spectroscopy as it is a branch of science that deals with the study of interaction of matter with light. So this light, it is nothing but the light contains, we know that it is electromagnetic radiations. So we can also define this spectroscopy as the interaction of electromagnetic radiation with the matter. So when the light falls on the particular matter, how it interacts with the matter. So here you can see this is the incident light which is falling on the matter, and what is happening to this light? It is either being reflected back, so that is known as reflected light, or it is getting absorbed into the matter. So when it gets absorbed, we call it as absorbed light. And after passing through the matter, some of the light will come out or it is transmitted out. So that light is transmitted light. So what happens when the surface of the matter is interacting with the light? So either it may get absorbed or transmitted, or it may get reflected or refracted. And this interaction depends upon the smoothness of the surface. That is the surface, whether it is smooth or it is curved or grated. And it also depends upon the nature of the material. So what is the type of the material that the matter is made up of? And also the angle of incidence. So if we change all these factors, generally the light which is transmitted out will also change, or the reflected light also changes. Now, as we are saying that the light is nothing but an electromagnetic radiation. So this energy radiation, it is in the form of packages of energy, which we call them as photons. And these photons, or the light, it travels in the form of a wave. And it is having two components. So it has both the electric field as well as magnetic field. Both these electric field and the magnetic field, they will be perpendicular to each other. So a photon, it consists of an oscillating electric field as well as the oscillating magnetic field, and which are perpendicular to each other. So here you can see that the magnetic field, the purple color, and the green is the electric field. So both are perpendicular to each other. So this is how the wave is traveling, which is having both the magnetic as well as the electric component in it. So when we are talking about a wave, then we need to know some of the terms which are related with it. So first we will know what is frequency. So frequency is defined as the number of lines or the number of waves that pass through a particular point in 1 second. So as you can see here, this is a wave. So starting from here and then going down and completing. So one complete wave, it will have one crest. So this is known as crest and this is known as trough. Okay, the lower depth is trough and the upper is crest. So one complete crest and one complete trough is a wave. Now how many waves travel through this particular point, this or any other particular point, is known as frequency. So frequency is nothing but the number of waves that pass through a particular point is known as a frequency. And the units of frequency are hertz. 1 hertz is equal to 1 cycle per second. So how many cycles are taking place in one particular second is nothing but the frequency. Then the other term is wavelength. So as we know here, you can see the picture, the wavelength is nothing but the distance between the two nearest crusts or troughs. So as I said, this is crust, this is another crust, this is another crust. Okay, so the distance between two near crusts. So the distance between two near crusts or the distance between two near troughs. So this is trough, this is another trough. So this is the distance between the two troughs. So the distance between two crusts or troughs is known as the wavelength. And its units are centimeter. You can take either, you can give it in nanometers or angstroms. Then what is amplitude? Amplitude is nothing but the height of the crust. So from the middle point here, this is the height of the crust, or you can either measure the depth of the trough. So from here, the depth of the trough. So the amplitude is nothing but it is the height of the crust or the depth of the trough. And it is denoted by A, and it determines the intensity of the beam of light. So higher the amplitude, so higher will be the intensity of the light. Then wave number. Wave number is denoted by nu bar. This is nu bar. So wave number is nothing but it is the inverse of wavelength. Okay, it is just the inverse of wavelength. Wavelength is lambda. So we can also write 1 by lambda is nothing but the wave number, or it is denoted by nu bar. It is expressed in centimeter inverse or meter inverse. Then velocity. So velocity is nothing but, now here we are talking the velocity of the wave or the light. So this velocity we can calculate it by a formula C is equal to nu lambda. That is C is equal to frequency as well as the wavelength. So it is nothing but the velocity of the wave or the light is equal to nu lambda. Now based on this, we can also derive an expression for energy of the wave. So how much energy does the electromagnetic radiation, a particular electromagnetic radiation is carrying? So as we know that C is equal to nu lambda. Now we have the energy relationship, which is E is equal to h nu. H is the Planck's constant. So here from C is equal to nu lambda, what will be nu? Nu will be equal to C by lambda. So this new value, if we substitute here, so it becomes h into C by lambda. So E is equal to h nu, or it is E is equal to hc by lambda. So this is how we calculate the energy of a particular electromagnetic radiation. So these are the terms what we have covered. That is what is the wavelength, amplitude, frequency, and what is meant by energy. Then as I said, electromagnetic radiation is nothing but it is a long, that is it consists of number of rays. You can see here gamma rays, X-rays, UV visible, IR, microwaves, and radio waves. Okay, so electromagnetic radiations consists of all these different types of rays. Now these rays are arranged in the order of wavelength or frequency or energy you can take. So in the order of the wavelength, suppose here you can see the wavelength of gamma rays is very less, 10 raised to -3 or -11 meters. So as you move on to the right side, that is when we are moving towards the radio waves. So what is happening to the wavelength? It is increasing. So wavelength increases as we move from gamma rays to the radio waves. These radio waves have higher wavelength. Now when we consider the energy, now energy is inversely proportional to the wavelength, because we have seen in the expression E is equal to hc by lambda. So energy is inversely proportional to wavelength. Now you can see the energy for gamma rays is around 10 power 8, whereas when we go towards the radio waves, it is 10 power -6. So what is happening? The energy is decreasing. So the energy of radio waves will be less when compared to the energy of gamma rays. Same as the frequency also. Frequency and energy are both directly proportional. So as the frequency is, you can see again from gamma rays to the radio waves, what is happening? The frequency is decreasing. Here it is 10 to the power of 7 hertz, whereas here it is 10 raised to 21 hertz. So gamma rays are highly powerful radiations which are having high energy, whereas the wavelength will be very less. Whereas the radio waves are having higher wavelength but less energy. So this is the electromagnetic radiation. Now how these rays, different rays will interact with the sample, that we have to see. Suppose if you are taking a prism and a white light is incident on it. So what happens? That white light undergoes scattering and it will give rise to different colors when you observe from the other side of the prism. So what are the colors we observe? It is Vibgyor, Vibgyor. So each letter stands for each different color. So V stands for violet, I for indigo, B blue, green, yellow, O for orange, R for red. So this is what Vibgyor. So Vibgyor is nothing but the scattering of the white light when it is entering into a prism. So when it enters into the prism, that white light is consisting of these many different wavelengths of different colors of light. Now among these you can see red light is having higher wavelength, 620 to 780 nanometers, whereas violet is having lesser wavelength, 400 to 420 nanometers. So here also the arrangement is based on the wavelengths. So red is having higher wavelength, violet has lower wavelength. So this light, when it falls on a particular molecule, so what happens is the atom, or that is the molecule, it can interact with the light and then it will give rise to a spectrum. Okay, so the spectrum is nothing but graph of intensity of absorbed or emitted radiation. So when the light is falling on a particular substance, it can absorb the radiations as well as it will emit also. So we can study the spectrum of both absorbed as well as the emitted. So the spectrum or the graph, whatever we get, will be on x-axis. We get will be taking frequency or wavelength, and on the y-axis we will be having the absorbed or the emitted radiations intensity. And the instrument what we use for the study of this spectra is known as spectrophotometer. Now, as I said that it may either absorb or emit the radiations. So first we'll see the absorption type of spectroscopy. So absorption spectroscopy takes place when a particular light will, when it goes and falls on a particular molecule, what happens is the molecule will absorb that light energy from the light, and the electrons which are present in the molecule, they will absorb this light and they get transited, or that is they get excited from the lower state to the higher energy state, or from the ground state to the excited state. So generally we know that all the molecules or the electrons will try to be only on the ground state or the lower energy level, because that will be the more stable thing. But when the molecule is absorbing energy, what happens, as it is absorbing, it can excite from the lower energy level to the higher energy level. So that absorption, study of how much energy of the light is absorbed for this excitation, is nothing but the absorption spectroscopy. So examples, all the UV visible light or IR light, when it falls on this sample or the molecule, they will get, or the molecule will absorb that particular wavelength of the light and transitions takes place. So these are the examples for absorption spectroscopy. Then the other one is emission spectroscopy. So what happens when it is absorbing? The molecule is moving towards the higher energy state. So after going to the higher energy state, the molecules will come back to the lower energy state. So when they are coming back to the lower energy state, some of the energy will be emitted out. So that particular light or the radiations which are emitted out, the study of that emitted light or the radiations is nothing but emission spectroscopy. So the spectrum corresponds to the radiation emitted when an excited electron returns to the ground state. So suppose if the electron which is present in the ground state is excited to the higher state, that is absorption spectroscopy. And when the electron is coming or when it is getting back from the excited state to the ground state, it is emitting some of the radiation. So the study of that particular emitted radiation comes under emission spectroscopy. So we'll see in this animation. So this is the introduction to spectroscopy. So this is the magnetic and electric fields of a wave, that is the light which is coming in the form of a wave. Now that light, when it falls on a particle, so some changes takes place, either the excitations or the emissions takes place. So that interaction of the light with the sample is known as spectroscopy. So spectroscopy is the study of interaction of electromagnetic radiation with the matter. So here the interaction takes place between the EMR, that is electromagnetic rays, and the matter. So it may be either absorption type or emission type. So first we'll see the absorption. So as I said, so this is the particle which is present at the ground state or the electron. So when it is absorbing some of the energy from the light, it is being excited. Okay, from the ground state to the excited state. So that is absorption spectroscopy. Then emission is from the excited state, it comes back to the lower energy level by emitting some of the radiations. So that is nothing but the emission spectroscopy. So what is the use of the spectroscopy? It is used for the study of the internal structure or the structure determination of any either organic or inorganic compound it may be. So if we look at the advantages of spectroscopy, it is less time consuming when we compare with the chemical methods. It is very small amount of sample is required and cost effective in the long run. First, if you want to purchase it, it is that is the cost is high, but it is very cost effective in the long run. So it is less time consuming, very small amount of sample is required. So this is the main advantage of spectroscopy. So that is the reason why we need to study the spectroscopy. So based on the radiations, what the matter is absorbing, we have different types of spectroscopy also. So first we'll see what is happening when the light is falling onto the particle or the matter here. So here we have different molecular energy levels. In any molecule, we'll find different energy levels, 3 different energy levels. One is electronic energy levels, vibrational energy levels, and rotational energy levels. So as you can see, electronic energy levels is having the distance between the electronic energy levels is very large when compared to the vibrational energy levels. Then comes the rotational. So these are the electronic energy levels, which are in turn consists of vibrational energy levels, and those vibrational energy levels in turn consists of the rotational energy levels. So here you can see delta E of electronic energy levels is greater when compared to vibrational and rotational. That means the energy required for the electronic transitions is high. Okay, the energy required for the electronic transitions, that is for the transition of an electron from one electronic energy level to the another electronic energy level, it requires high amount of energy. Whereas for rotational, it is very least because the space between the rotational energy level is very small. So less amount of energy is required for the excitation of electron between the rotational energy levels. Now, based on that, we have electronic energy levels, as I said. So at room temperature, most of the molecules will be at the lowest energy level, that is E0. Now, when the molecules are absorbing light, suppose if it is UV visible light, so what happens is the electron will be promoted to the higher energy level. So from E0, that is E0 is the ground state electronic energy level, and E1 will be the first excited electronic energy level, E2 will be the second excited electronic energy level. So from E0 it may go to E1. So that is what happens in the when the light when we are exposing the sample with UV visible light. Then the next one is vibrational energy levels. So these are less energy than electronic. Just now we have seen in the diagram. So the electronic energy levels, that is the vibrational energy levels, are having less space when compared to electronic. And the spacings are 0.01 to 10 kilocalories per mole. Now when this IR radiation is observed, suppose a molecule is exposed to IR radiation, what happens? So molecules are excited from one vibrational level to the other vibrational, but it will not go from one electronic to the another electronic energy levels. Okay, only the transition is taking place between the vibrational energy levels. Third one is rotational energy levels. So these energy levels are quantized and discrete, and the spacing between energy levels are very small when compared to vibration. So delta E of rotational is very less when compared to all the other two. Okay, so less amount of energy is required for this rotational energy transitions, energy level transitions. So again, the same picture I'm showing you. So electronic energy levels from E0, from suppose if this is E0 to E1. So from here to here, if the transition from here to here, the transition is taking place where you can see that the energy difference is large. Okay, so high energetic radiation such as UV visible, they can only that is if the sample is radiated with UV visible radiation, then only such type of transitions takes place between the electronic energy levels. Okay, then suppose if it is irradiated with IR, so IR radiations, only the transitions takes place in vibrational energy levels from V0 to V1. Then if it is suppose microwave region, which is having very less energy, that means the transition takes place only among the rotational energy level, these small lines, okay, from R0 to R1. So again, we can just have a look at it, different types of molecular spectra. So this is the molecule where it is interacting with the light. So we have different energy levels. So as I said, electronic, vibrational, rotational. So the red one is electronic, the blue is vibrational, and still that vibration consists of rotational. So particular wavelength of light is necessary for the transition to take place. And this is EMR spectrum. It consists of different rays. So based on that, we can have different types of molecular spectra, pure rotational, then vibrational rotation, and electronic band spectrum. So first, rotational spectra. So suppose a very less energetic radiations such as microwaves is interacted with the sample. What is happening? Only rotation is taking place. So the excitation we can see between the rotational energy levels only. Okay. So this such type of low energetic radiations we find in far IR and microwaves. So this spectra is known as microwave spectra. Then if the energy of the light is little bit more when compared to microwave, that is IR, you can see transition between vibrations, energy levels. So here rotational as well as vibrations takes place. So it is known as vibrational and rotational spectrum. And this amount of energy you can study with near IR. So this is known as IR spectra. Then electronic band spectra, where high amount of energetic radiations are required for this because the transitions takes place between the electronic energy levels. So in this case, rotation as well as vibrations takes place. So vibrational and rotational energy levels also, they are also part of this. So that will appear as a band. Okay, so that is why it is known as electronic band spectra, because the transitions are taking place even in the rotational energy levels, vibrational as well as rotational. So UV visible spectra comes under this category. Then, so till now we have seen the what is spectra, what is spectroscopy, that is the interaction of electromagnetic radiations with the matter, and it may be either absorption or emission spectroscopy. And then we have seen different energy levels, molecular energy levels. Okay, those are that is electronic energy level, then vibrational energy level, and rotational energy level. Then now we'll see how what happens actually to the intensity of the light when it is interacting with the sample solution. So a scientist named Lambert's, so what he observed was when a monochromatic radiation is passed through a solution, the decrease in the intensity of the radiation with the thickness of the solution is directly proportional to the intensity of the incident light. That is Lambert's law. So that I'll tell you. So here in the diagram you can see. So what he says is when a light which is being incident onto the solution with the incident light, that is I naught here, when it passes through the solution and as it comes out, that is when it is transmitted out, you can see the intensity is being decreased. Here you can see a dark color, dark blue, where it is here you can see the faded one. So that is nothing but to show the difference in the decrease in the intensity of the transmitted light. Okay, so that is dependent on the path length of the solution. So the thickness of the or the path length of the solution. So what the Lambert's law states is the decrease in the intensity of the transmitted light is directly proportional to the path length of the solution. Okay, so when we are saying that the intensity is decreased, so we will have to write it in the form of formula. So small decrease, that is minus di by dx. Suppose if we are considering x as the path length, will be directly proportional to I. Okay, so the decrease in the intensity across the path length is directly proportional to the intensity of the light also. So now this is nothing but by removing this proportionality constant, you can write it as Ki. K is constant. Then if we do integrate the equations between the limits I equal to I naught at x is equal to 0 and I equal to L actually and x is equal to L. So here what we get is the formula ln I by I naught is equal to minus KL. I is the intensity of the transmitted light. I naught is the intensity of the incident light. So by removing this ln, that is we can write it in 2.303 log I by I naught is equal to minus KL minus Y minus because the intensity is being decreased. Then log I by I naught is equal to K by, if you take this 2.303 to the other side, it goes to the denominator, then where log I naught by I is equal to absorbance. So here this negative, if we just remove, and this will become, that is the numerator becomes denominator and denominator will become numerator. So it becomes log I naught by I. So that we are taking it as absorbance. And K by 2.303, this term, we are considering it as a constant, and it is absorption coefficient epsilon. Actually it should be epsilon. So A will be equal to epsilon L. So this is nothing but the Lambert's law expression. So absorbance is equal to epsilon into multiplied with L. That is the length of the tube or the length of the solution, path length. So in this case, we need to know these terms are very important. That is absorbance, absorption coefficient, and there is one more word, that is transmittance. So this is about Lambert's law. So according to Lambert's law, now the absorbance is directly proportional to the path length. So when you increase the path length, so what happens? The absorbance will increase. Why it increases? Because when the path length is increased, what happens? More number of molecules will be present, where that is the light can interact with more number of molecules. Suppose if it is passing to one particular path, so here you can see, if we increase this length, okay, more number of molecules will be there to interact with the sample, to the with the incident light. So that's why absorbance will be more. So that was with the Lambert's law. And the other scientist named as Beer. So what he proposed is, it is not only, it depends, that is the intensity, decrease in the intensity of the light not only depends upon the path length, it also depends upon the concentration of the solution what we are using. So concentration of the solution means here, suppose, so what he has stated is, when a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with the thickness of the solution is directly proportional to the intensity of the incident light as well as the concentration of the solution. So the intensity, whatever it is, the transmitted light decrease is there, it depends upon the, that is, it is directly proportional to the incident light as well as the concentration of the solution. So the same thing we can write like this: decrease in intensity, that is minus di by dx, is directly proportional to the concentration as well as the intensity of the incident light, so into Ci. So if we remove the proportionality constant, it becomes equal. So we are writing K prime there, it is a constant. Then again, if we do the same thing, integration, so we'll get ln I by I naught is equal to minus K prime Cl. Okay, now again converting this ln to the logarithm, we'll get 2.303 log I naught by I is equal to KCl. Then just interchanging, 2.303 goes to the denominator there. And then log I naught by I, as we said, it is nothing but the absorbance. Then K by 2.303 is epsilon, that is molar extinction coefficient. We are calling here it as molar extinction coefficient, which is constant for each and individual solution. Then A is equal to epsilon Cl. So this is the final equation for Beer's law. Okay, so it says that absorbance is directly proportional to the concentration of the solution as well as the path length of the solution, right? So the combination of these two laws is nothing but the Lambert-Beers law or Beer-Lambert's law. It states that A is equal to epsilon Cl. So this is the equation you have to keep in mind. So according to this equation, we have different terms we have to define. So absorbance is, you can see, it is directly proportional to the concentration as well as the path length of the solution. So as I said, there is another term which is transmittance. So after the solution, suppose the solution is absorbing a particular amount of light, some of the light will be transmitted out. Okay, so that is nothing but transmittance, and it is defined as the ratio of intensity of transmitted light to that of the incident light. It is nothing but reverse of absorbance. Okay, so T is equal to I by I naught. So I is what? Intensity, this I is intensity of transmitted light, whereas I naught is intensity of the incident light. Okay, so it is having no units because it is a ratio of transmittance of the lights only. So as the concentration of solution and the length of the medium increases, the intensity of the transmitted light goes on decreasing. So why it decreases? Tell me. So that means here, so as the concentration is increasing, okay, as well as the length is increasing, what is happening to the absorbance? Absorbance also increases. Okay. So why? Because the concentration increases means number of molecules which are present in that particular solution is increasing, as well as length, path length increases means the number of molecules which are interacting with that incident light also increases. So therefore the absorbance also increases. So when absorbance is increasing, the transmitted light will be less. So that is the reason why the transmittance is always inversely proportional to the absorbance. So when absorbance increases, transmittance decreases, or when absorbance decreases, transmittance increases. So that is what, again, the absorbance, the negative logarithm of transmittance is called absorbance. So A is equal to minus log T, or A is equal to minus log I by I naught. This is I by I naught is what? Is the transmittance. Okay. So now if we just remove this negative charge, so just the two terms are getting reversed. So A will be equal to log I naught by I. So this is the formula to calculate the absorbance. So that's what I said. So absorbance and transmittance are inversely related. Okay. So absorbance increases with increase in concentration of the solution and the length of the medium, because A is equal to epsilon Cl. That equation you need to remember. Then how to define molar extinction coefficient, that is epsilon. And it is defined as the absorbance of a solution with 1 centimeter thickness and 1 molar concentration. So that means when the concentration is 1 molar and when the path length is 1 centimeter, that is nothing but E will be equal to A. So from Beers-Lambert's law, A is equal to epsilon Cl. Okay. So E will be, that is epsilon will be equal to A by Cl. So C, as you know, what is C? C is the concentration, which is expressed in moles per liter. L is path length, which is expressed in centimeter. And A is the absorbance. So as I said, if length is 1 centimeter and concentration is 1 molar, then what happens? E will be equal to A, because the C and L, we are making it unity. That means E is equal to A. And the units of epsilon are liter per mole per centimeter. So this is what Beer-Lambert's law says. A is equal to epsilon. Actually, it should be this one, that is epsilon Cl. That is nothing but log I naught by I, where C is concentration in moles per liter. L is length of the path through the cell. So this is the cell, the length, how much it is traveling. And epsilon is molar absorption coefficient. So this is how we record in the that is how what is the transmittance and the absorbance we record in the spectrophotometer. So this is a source where the light falls, and only monochromator, it is passing through the monochromator. So the use of monochromator is only particular wavelength of the light is selected, and then that wavelength is being incident into the sample. Here it is the cell or cuvette. That means that is cuvette, which is made up of glass or quartz. In this, we will be taking the sample solution. Okay, the incident light is made incident onto the sample solution, and this is the transmitted light. That light will, when it falls onto the detector, it will give rise to a signal. Okay, so this is all about Lambert-Beers law. So just we'll once again go through. So this is a spectrophotometer. As I said, it is used for the determination of the spectra. So the light source falling onto the sample. Okay, so sample, that is the cell or the cuvette. So the light source from where it is falling onto the diffraction grating. So a particular wavelength of the light can be selected and it is passed through the exit slit. From there it interacts with the sample and it is detected. So whatever the that is the light. Suppose if it is transmitted light, that will be detected on the detector. That is we call it as transmittance. And suppose the amount of the absorbed light, that can also be determined by the spectrophotometer as the absorbance. So all these lights, either it may be transmitted or absorbed light, it will be displayed on the it will be displayed on the instrument. Okay, so so just once again you can look at it. So the light source that is falling on the gratings, so that grating can be rotated so that any particular light can be, wavelength of the light can be selected, and that can be passed through the slit. This whole thing is nothing but monochromatic. So light falling onto the sample and that is being detected by the detector. So it may be either transmitted light or the absorbed light. So it shows a signal. It will give both the readings. If you want the transmittance, you can just, there's a knob there. So only you will get a transmittance. What is the percentage of transmittance, or either you can get in the absorbance also. So as I said, so what is Beer-Lambert's law? It is nothing but A is equal to epsilon CL. So absorbance is directly proportional to the concentration. Okay, so when we draw a graph by taking concentration on x-axis and absorbance on y-axis, we need to get a straight line like this. Okay, ideal straight, that is a straight line which is passing through the origin. Okay, so that means we say that it is satisfying Lambert-Beers law. But there are some deviations to this law. There are positive as well as negative deviations. So positive deviation, you can see this red curve. So why the red curve is appearing? Because as the concentration is increasing, there should be proportional increase in the absorbance. That means we should actually get a straight line there. But what happens is sometimes as the concentration is increasing, there is a large increase in the absorbance. So that is giving rise to positive deviation. And the negative deviation is, as again the concentration is increasing, what is happening to the absorbance? It is increasing slowly. Okay, so that means it is giving rise to a negative deviation. So that is the reason why we need the solutions to be dilute solutions. So only the dilute solutions will give rise to the correct exact straight line which passes through the origin. Then what are the limitations? The last part is the limitations. So as I said, so there are some deviations with this. So these deviations may be due to some chemical as well as instrumental factors. So one is about the high concentrations. All the samples should be at a low concentration. Suppose if it is exceeding 0.01 molar, okay, then we find some deviations. So due to that deviations, we cannot easily calculate the lambda max value and the absorbance, everything. So we need to see that the solution is dilute, and there should not be scattering or fluorescence or phosphorescence also. So these are some of the instrumental as well as the chemical. It's not exactly chemical, but some of the light, it undergoes scattering, and sometimes fluorescence, phosphorescence can also be seen. So that is also one of the limitation of this law. So change in refractive index at high analyte concentration. So high concentration of the sample will also change in the refractive index. So hence the solution should be taken in a low concentration. That means it should be diluted. So this is about Lambert's-Beer law. So what is the formula we need to remember is A is equal to epsilon CL. A stands for absorbance. Epsilon means molar absorption coefficient. C stands for concentration of the solution, and L stands for the path length of the solution. So in today's class, we have seen what is spectroscopy. So two types, that is absorption as well as emission spectroscopy. So what are the different molecular energy levels? So what are they? There are three types. Those are electronic energy levels, vibrational energy levels, rotational energy levels, and then we have seen this Lambert's law as well as Beer's law. So combining together, it is Beer-Lambert's law and the limitations. So thank you for watching. Hope you have understood the topic. See you later. Bye.